There is a way to go a little bit faster by using the LCD to simplify these complex rational expressions. The way you work that is that first you find the LCD of the smaller nested fractions. And what I mean by that are the fractions within the overall fraction. So in this first example where I have 5 plus 1 over x minus 1, and then in the denominator 1 over x minus 1 minus 1/4, what I have here are 1, 2, 3, 4 kind of nested fractions. And I want to work with those in terms of thinking about their common denominator. So I'm going to find the LCD of them. The second thing is that I'm going to go ahead and multiply both top and bottom of the big fraction by the LCD I found for those smaller nested fractions. So let's go ahead and do that for this example. So I know I kind of wrote over these fractions, but hopefully you can see that I have 5 over 1 plus 1 over, and this was an x minus 1. So I have an x minus 1 as a common denominator in the numerator, but I also have the x minus 1 in the denominator and then a 4. So the LCD is going to be 4 times x minus 1. I'm going to multiply this entire fraction by 4 times x minus 1 on both top and bottom. And the reason this is valid, and it's an okay thing to do, is that technically I'm multiplying by something over itself, so I'm multiplying by 1. So I'm not changing the value of this complex fraction by multiplying by the LCD over itself. Now, here's where you have to be careful. When I multiply this through, I'm going to multiply it to every term in the numerator and every term in the denominator. And until you get used to this, it's a good idea to just write it all out. I'm going to give myself even more room than I started with. So I'm going to show what happens here. So I'm going to have a 5 times 4 times x minus 1. So I distribute it to the 5. And then I'm going to have plus 1 over x minus 1 times 4 times x minus 1. In the denominator, I'm going to have 1 over x minus 1 times 4 times x minus 1. And then minus 1/4 times 4 times x minus 1. So you'll see that that 4 times x minus 1, which was the common denominator, ends up going into every term in the numerator and denominator. It looks really complicated right now, but there are things that can be canceled. In fact, the reason we chose the LCD is that it's going to allow us to cancel all of these smaller denominators, because technically this is the LCD over 1, and I can cancel x minus 1's here. I can do the same thing down here. X minus 1's cancel in that first fraction in the denominator. And then in the second term in the denominator, it's the 4 that cancels. So if you look carefully, my smaller fractions, all of the denominators have canceled out. So if I look at what's left, I have 5 times 4 times x minus 1, which is just 20 times x minus 1. So I could distribute that, 20x minus 20. And then in the next term in the numerator, I have a 4 left in the numerator, and that's it. So plus 4. And in my denominator, I have 4 left in the first term, and then minus 1 times x minus 1. So x minus 1 is subtracted entirely. So I'm going to need to distribute that minus. So I have 20x minus 16 on top over, and then if I distribute the negative, I have negative x plus 1, and then I've got a 4, so that's plus 5. So I collected like terms as I distributed that negative. Now you might say that looks really messy, and it does. This step is nasty if you write it all out. But a lot of times what people do is they get used to canceling as they go. So they'll do a combination and end up down here by doing some of the canceling in their head. You're welcome to do that. Just be very careful. And maybe the first few times write it out. Now we did do a cancelization here. So we should show domain restriction. So if we go back up, what we canceled was the x minus 1. That had a variable. We also canceled the 4, but the 4 has no variable. So with that x minus 1, we should show that x cannot be equal to 1 as our domain restriction for that simplification. Let's do this one more time with the LCD. In our next example, we have a big fraction with two nested fractions in the top and two nested fractions in the bottom. The two nested fractions in the top both have a common denominator of a, basically, so I'm going to have a in my LCD. In the bottom, I have more than just a, though. I have a denominator of a minus 2, so I need an a minus 2 in here. And I have a denominator of 3, so I need a 3. And typically we put a constant out front in our factorizations. So I'm going to use an LCD of 3a times a minus 2. So I'm going to multiply both top and bottom by 3a times a minus 2. Now, this time, as I write it down, I'm going to simplify as I go. So I'm going to distribute this to both terms in the numerator. Now, when I distribute this to both terms in the numerator, this a right here is going to cancel with the a's that were in their denominators. So I'm going to end up with the 1 multiplied by 3 times a minus 2. What's left when this a cancels out? Plus the 2 that's in the second numerator in that top, that's going to be multiplied as well by 3 times a minus 2. So basically I'm canceling those smaller denominators as I distribute the LCD in. We can do the same thing in the bottom. Distribute this 3a times a minus 2 into those two terms in the bottom. Now in the first fraction, we have an a minus 2 in the denominator, which is going to cancel with our a minus 2. So what's left is I'm going to have 1 times just 3a. And then I have a minus, and then the a over 3, the 3 is going to cancel with my LCD. So I'm going to still have the a, and then I'm going to still have the a times a minus 2 from the LCD. So simplifying this now that I no longer have those nested denominators, I need to multiply everything out and then collect like terms. 1 times 3 in the top is just 3, times a minus 2 is 3a minus 6. 2 times 3 is 6, and then distribute the 6 through. 6 times a is 6a. 6 times negative 2 is negative 12. In the bottom, do the same thing. 3a, and then minus a squared. A times a is a squared. Distribute the a squared through. A cubed, and then minus a squared times a negative 2 would be plus 2a squared. Now let's collect like terms and write things in descending order. In our numerator, we get 9a minus 18. In our denominator, we have negative a cubed plus 2a squared plus 3a. At this point, we've collected like terms in the numerator and denominator, so the only thing left to do would be to try to simplify. To do that, we would try to factor. There is a common 9 in the numerator. We'd be left with a minus 2. And the denominator, I could factor a negative a out to get a squared minus, watch your signs there, because I'm taking a negative out of a positive, I'm going to get negative 2a, and then minus 3. Now I could continue to factor this trinomial right here, a squared minus 2a minus 3. It would factor, but I'm going to get factors of a minus 3 and a plus 1, which doesn't cancel with anything in my numerator. So technically, because there is no common factors here, I would just end right there. That would be my final answer. And I did cancel up here the a's from the denominator. So up here, I did cancel this a, so a cannot be 0. And I also canceled up here a minus 2's, so a cannot be equal to 2. So I need to show that in my final statement. A cannot be 0 and a cannot be 2, because I did do the cancellations up here. Although right here I have an a in the denominator, so technically I don't need the 0. I just need to show that a is not equal to 2. I already know that a cannot be 0, because the a is in the denominator. So clarification there, I only technically have to show that a cannot be 2 because of the cancelization I did up at the top. So that's the second technique for simplifying complex rational expressions. It's your choice when you do homework problems whether you use order of operations or this LCD shortcut.